In this video, I consider countable sets. I have already explained denumerable sets and countable sets. When you say that set is denumerable, set is denumerable. A set capital A is said to be denumerable if it is equivalent to n, set of natural numbers. Equivalent to n means, when you say that set A is equivalent to n, if there exists a function n from A or A from n which is 1 1 as well as on 2 bijection, then A is said to be equivalent to n. Then A is said to be denumerable. What do you mean by countable set? Countable means a set is said to be countable if it is either finite or denumerable. What are the results we have already studied? First one is, if A and B are countable, A and B are denumerable, then A union B is denumerable. Correct? A and B is denumerable. Second, if A is denumerable, and A is equivalent to B, then B is also denumerable. Once I state the important results that we have already studied. Next I continue the different results on countable sets. First is, if A and B are denumerable, A union B is denumerable. Second, A is denumerable and A is equivalent to B, then B is also denumerable. Next is, every subset of a countable set is countable. Countable set is countable. This was an important theorem that we have proved. Every subset of a countable set is countable. We have divided the proof into different cases and we have proved this one. Go through that, it is important. Now immediate corollary to this result is, every infinite subset of a denumerable set is denumerable. Denumerable set is denumerable. And finally, if an infinite set has a denumerable subset. These are the different results that we have already studied. Say 5 results we have studied. Now today I first prove one important result that is used to prove that some sets are countable. The result is like this. I take this as a theorem. Theorem is like this. If A is denumerable, and f from A to B is injection. What do you mean by injection? Injection means 1 1 function. If f is 1 then it is called injection. On 2 is called surjection, and 1 to 1 is called bijection. Both 1 1 as well as on 2 is called bijection. See, the result is like this. If A is denumerable, f from A to B is injection, then f of A is denumerable. Now this is important tool here which is helpful while proving certain sets are countable or sets are uncountable. We use important tool. What is the theorem? First to understand this one, if A is denumerable, f from A to B is 1 1, then f from A is denumerable. What we prove is, if A is denumerable, and important thing is this, if f from A to B is injection, then we prove that f from f of A to B, f of A to or 1 minute, if f from A to B is injection, we prove that f from A to f of A is onto. See, the proof is like this. Very important result it is. If f from A to B is injection, always f from A to f of A is onto, that is surjection. Therefore, f from A to f of A is, it is bijection. It is bijection. Therefore, A is equivalent to f of A. By definition of equivalent sets, when you say that two sets are equivalent, there exists a bijection. A is equivalent to B means there exists a function f from A to B which is bijection. Now, if f from A to B is injection 1 1, always f from A to f of A is, it is surjection. Onto means surjection. Therefore, f from A to f of A is 1 1 as well as onto, therefore bijection. What does this imply? This implies A is equivalent to f of A. Therefore, A is denumerable means f of A is also denumerable. This is the proof. How do you prove this one? The important thing is, if f from A to f of A is f from A to B is injection, that is 1 1. F from A to f of A is onto. I take some diagrammatic representation. Simple example. Suppose A is 1 2 3 4 and B is A B C D E F. F will be defined as A to B is function is 1 1. What do you mean by 1 1? 1 1 means, the broad sense, 1 1 means different elements have different images. Therefore, I take 1 is related with A, 2 with B, 3 with D, 4 with E. Then it is strictly 1 1. Here, what is f of A? I take f of A now. F of A means it is the set of all images under the function f. It is f of A. F of A is only images you have to take. A, B, D, E. What is it? 1, 2, 3, 4. Now, under F, A is related with 1 is related with A, 2 is related with B, 3 is related with D, 4 is related with E. Now, if you consider only F of A, not all B, we consider only F of A. What is this now? A to F of A is, it is onto. What do you mean by onto? If all the elements of the codomain are the images, then it is called onto. Here, if here f from A to B is 1 1, that is injection, then f from A to f of A is surjection. So, what is f from A to f of A? F from A to f of A is bijection. Therefore, this A is equivalent to f of A. A is equivalent to f of A. Therefore, what happens? If A is denumerable, f is only 1 1, then A is equivalent to f of A. A is equivalent to f of A. Therefore, if A is denumerable, f is only 1 1, then f of A is denumerable. Important result it is. I hope all of you understood this one. Now, I explain how this result is applied in important theorems. The theorem is, very important theorem is this. Every year this theorem is asked. for the board university examination. Theorem states like this: n cross n is countable. N cross n is countable. Here notation are standard. N means set of natural numbers. N cross n is countable. You know what is cross product? N cross n. What does n cross n consist of? N cross n consists of all the parts AB, where AB are natural numbers. Set of all order is AB. N cross n. Now we used the previous theorem here to prove that n cross n is countable. We use this one. Define proof of this. Define f from n cross n to n cross n to n by f of mn is equal to 2 raised to m into 3 raised to n. This definition is important. Here, what is the domain? Domain is n cross n. This is domain. What is codomain? Set of natural numbers. What are the elements of the domain here? They are the order pairs. Therefore, I have taken f of m1 comma n. Means the domain consists of order pairs mn. And what is the codomain? Codomain is set of natural numbers. It consists of only natural numbers. But domain consists of order pairs. How the function is defined? F of mn is 2 raised to m into 3 raised to n. Now we prove that. First we prove that f is injection. Injection means 1 1. F is 1 1. For that, when you say that function is 1 1, a function f from a to b is said to be 1 1. If f of x is equal to f of y implies x is equal to 1, then the function is said to be 1 1. Now I take f of, for that, to prove that f is 1 1 or injection, let f of pq is equal to f of rs. Then what you have to prove? pq is equal to rs. Then it becomes 1 1. What do you mean by f of pq? 2 raised to p into 3 raised to q, because by this definition. What is f of rs? 2 raised to r into 3 raised to s. Now by unique factorization theorem, what does unique factorization theorem states? Here 2 raised to p, 3 raised to q is 2 raised to r, 3 raised to m. S implies by unique factorization theorem p is equal to r, q is equal to s. Therefore, order pair pq is equal to rs. So f of pq is equal to f of rs implies pq is equal to rs. Now what does this implies? This implies f is 1 1 injection. Now what is the previous theorem? If f from a to b is injection, then a is equivalent to f of a. This is the theorem. Correct? Therefore, what is a here? N cross n is equivalent to f of n cross n. Correct? N cross n is equivalent to f of n cross n. But what is, this is from previous theorem. What is f of n cross n? F of n cross n means the images of this function. What are the images? Images lies in n. Correct? Images lies in n. Therefore, but f of n cross n is, it is subset of n. Correct? F of n cross n belongs to n here, subset of n. But what we have proved? Every subset of denumerable set is denumerable. Now here n is denumerable. Since every subset of denumerable set is denumerable f of n cross n is denumerable. Now if f is injection from n cross n to n, then n cross n is equivalent to f of n cross n, but f of n cross n is subset of n, therefore it is denumerable. F of n cross n is denumerable. Now see this step, n cross n is equivalent to f of n cross n, therefore n cross n is denumerable. N cross n is denumerable, therefore countable. So n cross n is countable. The main idea is this: we have defined function from n cross n to n, and it is 1 1. The function is 1 1. If function f from a to b is 1 1, then a is equivalent to f of a. N cross n is equivalent to f of n cross n. But f of n cross n is subset of n, and this n is countable. N is denumerable, or you can write countable here. Therefore, every subset of a countable set is countable. In the beginning only I explained, we have proved many results. This is one of the results. Every subset of countable set is countable. Therefore, f of n cross n is countable. But what is f of n cross n? Equivalent to n cross n. If a and b are two sets, so that a is countable, then b is also countable. Therefore, n cross n is countable. Important result it is. So we have proved that n cross n is countable. Next theorem is the set of all rational numbers is countable. All these results are important. See, I have used one technique here to prove that n cross n is countable, but there are many different methods to prove n cross n is countable. I have chosen this is one of the best method to prove that n cross n is countable. Similarly, the set of all rational numbers is countable. Many different methods are there to prove that rational numbers is countable, but I used that theorem. What is that theorem? If a is countable and there exists a function f from a to b which is injection only 1 1, then f of a is also countable. We use that result. Here, set of all rational numbers is countable. What is the set of all rational numbers? It is denoted by q. We write q as set of positive rational numbers union 0 union negative rational numbers. Q means set of all rational numbers. How to define q? Set of all rational numbers p by q form, where p q are integers, q not equal to 0. This is the definition of rational numbers. Now we take q as union of positive rationals, negative rationals and 0. Now first we prove that q plus is countable. For that, define f from q plus 2 n cross n. See, the previous result we have proved n cross n is countable. We make use of that one. Define f from q, f from, not f of q plus, f from q plus 2 n cross n by f of p by q is, what are the elements of q plus? they are of the form P by Q. It is f of P by Q is PQ, order pair PQ. Because there are two sets here, domain Q plus C, set of all rational numbers, they are of the form P by Q. And n cross n means n cross n is it is order pairs. And I think you have followed the elements of two sets here. What are the types of the elements? Q plus consists of P by Q form, and that n cross n consists of order pairs. So define f of P by Q is equal to PQ. Now what you have to prove here? You have to prove that it is injection. F is injection or 1 1. How to prove this one? Let f of P by Q is equal to f of R by S. P by Q, R by S are both positive rational numbers. This implies order pair PQ is equal to RS. Order pairs are equal means corresponding coordinates are equal. P is equal to Q, R is equal to S. Therefore, P by R is equal to Q by S. P by R means, what is P by R? P by R is equal to Q by S, or P is equal to Q, R is equal to S. Correct? P by Q is equal to not P is equal to Q. 1 minute. What happened here? PQ is equal to RS. Order pair means P is equal to R, Q is equal to S. Therefore, P by Q is equal to R by S. So f of PQ is equal to f of R by S implies P by Q is equal to R by S. What does this implies? This implies this. What is this? What is that? F is injection. 1 1. F is injection means this Q plus is equal to f of Q plus is equivalent to f of Q plus. Correct? But what is f of Q plus? F of Q plus is subset of n here. Because see the elements, f of Q plus is subset of not n cross n. It is subset of n cross n. Since n cross n is countable, subset of a countable set is countable, f of Q plus is countable. F of Q plus is countable, therefore Q plus is countable. Q plus is countable, similarly we can prove that Q minus is countable, 0 is countable, union of countable sets is countable, therefore Q is countable. Yes, thank you. I will continue in the next video.